Next, we are going to look at a spring design problem for static loading condition. This is example problem 10-2. What we have over here is a music wire um, using which we are making a helical compression spring. The spring needs to support a load of 89 newtons. So F max is going to be 89 newtons. For this particular load, we would like it to be compressed by 50.8 mm. The solid height cannot go beyond 25.4 mm, and the overall length, free length L naught, has to be less than or equal to 101.6 mm. So within these constraints we need to design the spring. Now the first thing that we need to come up with is going to be the wire diameter. The wire diameter, a priori we don't know what it is, so we'll have to start with something. So for example, let's say we write a program where this can be incremented in a certain manner. So let's say we are going from 1.6 mm to 2.4 mm in increments of 0.1. So let's say initially we start with 1.6 mm. Now since we are dealing with music wire, then from table 10-4, uh, we can find these parameters A and M, and then get the ultimate tensile strength of the music wire to be 206 sorry 2065.34 MPa. Please note that in the case of springs, the ultimate strength of the material depends upon the diameter of the wire that you are using. This strange dependence comes from the fact that wires are typically cold drawn uh, before they are coiled into springs, and because of this cold working there is a increase in strength of the material. So smaller the wire diameter, more the amount of cold working, and higher the strength of the material. Now once you know the ultimate tensile strength, then you can get to know the shear yield strength of the material from table 10-6. Over here you need to know whether there is some presetting or there is no presetting within the spring. Nothing has been set, so by default we assume that there is no presetting of the spring, because of which the relation between the shear yield strength and ultimate tensile strength is going to be this. So the shear yield strength is taken to be 45% of the ultimate tensile strength of the material. Again, this comes from table 10-6. So in this case, the shear yield strength is 929.4 megapascals. Now, nothing is said about the safety factor. So we are going to assume the safety factor to be 1.2. And with that, we get alpha to be which is actually the ratio of the shear yield strength to the safety factor, to be 774.5, and beta, which is defined through this relation, to be 101.81 MPa. So we are taking this factor psi, uh, which finally relates F max to the force needed to take it to the solid length. We take that psi to be 0.15, and based on this we get the value of beta to be 101.81 MPa. So from here, using this relation for the spring index, we get the value of the spring index to be this 6.18, and through that we can estimate the outer diameter of the spring, sorry, the mean coil diameter to be 9.9 mm and outer diameter to be 1.5 mm. Now once you have this information, you can go ahead and determine the number of active coils which are required in order to cause a deflection of 50.8 mm for a load of 89 mm. So using the information for the shear modulus of the wire diameter, deflection, mean coil diameter, and the maximum force, we get the active coils to be equal to 39.85 rounded off to 40. Now and also the solid length, it's a squared end condition, so the solid length will be active coils plus 2 times the wire diameter, which comes out to be 64 mm. and the free length would be equal to the solid length plus 1 plus psi times y max. It comes out to be 122.42 mm. Now L naught critical in this particular case, it turns out to be 2.63 times 9.9 by 0.5 to be 52.074. Okay, so now for this particular choice of wire diameter, we are violating several constraints. First, the active coils is too large, 40. Then the length of the free length of the spring is turning out to be larger than the length for which buckling is avoided. So for all these reasons, this is not a valid consideration. So now we would have to increase the wire diameter. So we keep doing this, and when we keep doing this, we'll see that if you choose a wire diameter of around 0.2 mm, then in this particular case the outer diameter would come out to be 21.3 mm in order to achieve that particular deflection for that particular force. The outer diameter will turn out to be this, C to be 10.5, and then Na to be 10.2, the solid length to be this, the free length to be this, the L naught critical to be 112, and over here now you can see that the spring index, active coils, they are all within the design ranges that we would like. The solid length is also not exceeding whatever is the criteria which has been set, and L naught is actually lower than L naught critical, so we are fine. So this is how you do the static spring design. So you start with a certain choice of wire diameter and wire material. You run through the steps, you see whether you are able to satisfy all the design considerations. If not, you change the wire diameter. You keep doing this until you hit upon a wire diameter where you satisfy all the design considerations. And among the wire diameters which satisfy the design considerations, you pick the wire diameter which requires the use of least amount of material.